Section 2.4 is going to cover some different statistical graphs beyond histograms. This first one's called a frequency polygon. Now, back in geometry, you learned about a number of different polygons, which are just different shapes. And we're going to take our frequency table and we're going to use it to make a shape within the graph. Now, it's a shape because it's a closed figure. It's going to start on the x-axis and end on the x-axis, so it makes this weird looking, almost mountain type shape. Okay, these points here, every point in the shape is taken from the frequency table. It's just the frequency of this class. All right, when we plot these, we plot those frequencies above the midpoint of this class. Okay, so 25.5 is just the midpoint of that 21 to 30, which we went over in the last section. Again, we do want these to be closed figures, so when we plot our frequencies above the midpoints, we always add one more point to the left of the leftmost midpoint, and we just connect it to the x-axis there. And same thing with moving to the right of the rightmost midpoint, connect it to the x-axis. That makes that bottom horizontal line close out the polygon. When we have two of these on the same graph, it allows us to compare the two fairly easily. So here we have actresses in red, actors in green, and we can see that males are winning Best Actor at a higher age than females are winning the Best Actress Academy Award. Also, when we talk about relative frequency polygons, that word relative is just telling us that we're going to switch everything to percentages. So this here is a relative frequency polygon. We can see that instead of counts on the vertical axis, we have percentages. This next one is a bit of an odd pronunciation. It's called an ogive, and this is a graph that's showing the cumulative frequency distribution. And we had talked about this when we were talking about frequency tables. Cumulative means we're just going to sum up all the frequencies that we've seen in the classes preceding the one that we're in. For example, if we're in class 31 to 40, okay, there's 30 in that class, and there were 28 in the class before it. We add those together to get that 58. Okay, this 72 comes from all of the frequencies that we've seen up to that point. Okay, this number here should just be the sum of the frequencies. Okay, and sometimes we're going to do relative frequency ogives, where we'll just switch all these numbers to percentages by dividing them by the total number of frequencies, in this case 76. So ogives are helpful in determining the number of values below some particular data value, okay, or the percentage of data below some particular data value. And when we make these, one of the things that differentiates it from the frequency polygon is we take these frequencies and we put them above the class boundaries, okay, where in the frequency polygon, we were plotting them above the midpoints. The graph always begins with a lower boundary, the first class. So we're starting with a lower boundary here, 20.5. And we haven't passed any of the data yet, so it starts at 0. And then it ends with the upper boundary. So once we're up here at 80.5, we've passed all of the data. That's where that 76 goes. This is a graph you should be familiar with. You've seen dot plots before. Just to note, when you make a dot plot, try to make all of your dots or X's or whatever you're using the same height. So when we stack them, we're abiding by the area rule. A stem plot is another graph that you've probably seen before. In a stem plot, we have a stem, which in this case is the tens digit, and then we have a bunch of leaves. So this really represents three different numbers. We have 64, take the stem, attach this first leaf here. We have another 64, since there's another 4 there. And we have a 69. Okay, so it just condenses them. We can see there's a whole bunch of numbers in the 70s. And when we look at a stem plot, we can see the shape of the distribution. Okay, so turning it on our side lets us see that a little better. We see a gap here. We see an outlier at the end. And one thing that you probably haven't done with stem plots is what's called a split stem or expanded stem stem plot, or a condensed stem plot. So in a split stem plot, you just take all of those numbers in 60s, and we're going to split them into two parts. So we have the 0 through 4 in this first 6, 5 through 9 in that second 6. Okay, so we can see we're splitting those up. 70s, same thing. So that first 7 is for the 0s through 4s, and then that second 7 is for everything from 5 through 9. So if we split them up, we get a better idea of what the shape of the distribution is. Okay, it's even more approximately symmetric, and we still have that outlier up at 120. Condensed stem plots is when we just take those stems and we smush them together. So we're combining them. So here we're putting the 6s and the 7s together. We want that shows where we're separating the two. If we have only a few numbers in each stem, that's when we would want to condense. If we have a bunch of numbers in each stem, that's when we would want to split them. A Pareto chart is a bar chart, and we know it's a bar chart because we have these spaces in between our lines here. We can rearrange a bar chart, unlike a histogram. The bars in a histogram touch each other because we can't rearrange those numbers. The only reason we would see a gap in a histogram is if there's a gap in the data. What's specific about a Pareto chart is we want them arranged in largest to smallest order. Pie charts are another one you've seen. This is for categorical data. We wouldn't ever make a pie chart of quantitative data. And if we actually want to construct a pie chart, just remember it's out of 360 degrees. So if we have our data in percentages, just take that percentage, multiply it by 360, and that's the degrees that it's using up of the circle. So 212 degrees, we know that's a little above 180. 180 would be a straight line, so kind of map it out like that. Scatter plots are for paired data. I'm going to circle that because as of the time of making this video, that's a question that's on the test. Paired data means we have two variables linked together. So like X and Y coordinates, maybe heights and weights for a single person. We use scatter plots to find the relationship between two variables. And lastly, the time series graph, also known as the time plot. This is really just another scatter plot. We're connecting them with lines to see trends. And it's a specific kind of scatter plot because the horizontal axis in a time plot is always time. In this case, it's year. So when we make a time plot, we can see trends if something's increasing over time, decreasing over time, etc.